Good morning, sir.
This meeting is being recorded.
Okay. Uh, Good morning to all of you. Screen is visible.
Yes, sir.
Okay. So before going to the next point, whatever we have discussed in yesterday's lecture, again we will revise it very briefly. Okay. So in yesterday's lecture, we have discussed about the static and dynamic behavior of CMOS inverter. Okay. So what do you mean by static behavior? So actually this static behavior we are analyzing to check the robustness of that particular device, right? So what are different parameters or what are different points that we should consider to analyze the static behavior of CMOS inverter? So first you must understand and analyze its voltage transfer characteristics. That means input voltage by output voltage. Then you must study the switching threshold. Then you must study or you must analyze the noise margin for that particular device. Okay. And for the dynamic behavior, why we should go for a dynamic behavior? So this dynamic behavior we should study to check or to analyze the performance of that particular device, right? Now what are different pointers or parameters that we should consider to get an idea of to get an idea for the performance of that particular device? In our case it's a CMOS inverter. So you must study and analyze different capacitances, parasitic capacitances, intrinsic and extrinsic capacitances, right? Then you must study the delays. Okay, you must study the different delays, propagation delay, right? It's a difference between the high to low transition of input and output signal to low to high transition of input and output signal. Okay, so that part we will discuss also. Now in VTC we have studied the different operating conditions. There are basically 5 region of operation in case of CMOS. In first region, NMOS is off, PMOS is in linear region. In second condition, right, or in a second region of operation, NMOS is in saturation and PMOS is in linear. Then in third condition, that means during this part of graph, NMOS and PMOS both are in saturation region for this third region of operation of CMOS. In case of fourth region, that means this particular part of graph, NMOS is in linear region, PMOS is in saturation region, right? Then in the fifth region of graph, NMOS is in linear region and PMOS is a off. That means cutoff region, right? So this particular thing, this voltage transfer characteristics between V in and V out, that also you must study, right? Now inverter switching threshold. Now see, this is not your normal VTH. Okay, what do you mean by this inverter threshold? The point of the this voltage transfer characteristics, the point where exactly V in is equal to V out, right? The point where V in is equal to V out. So this particular point lies between exactly middle of this voltage transfer curve or voltage transfer characteristics between V in and V out. And if you plot a linear line, if you plot a linear line between this plot, you will get the exactly symmetric architecture or this symmetrical curve between this separation line, right? This line indicates V in is equal to V out. That means there is a linear relationship between input and output. So and this point or this particular point is called as switching threshold of inverter, right? Switching threshold of inverter. So this parameter also you should consider while studying the CMOS inverter. Now coming towards the noise margin, right? As you know, what do you mean by noise margin? So basically noise margin is the amount of noise that a CMOS circuit could withstand without compromising the operation of circuit. That means the amount of noise that the circuit can bear without degrading its output. समजते? म्हणजे amount of noise that circuit can bear or circuit could withstand with, right, without compromising the operation of circuit. म्हणजे इनपुट वर कुठला इफेक्ट होणार नाही, पण तो नॉइज सुद्धा तेवढा तो सर्किट बिअर करू शकतो किंवा अलाव करू शकतो. त्या पर्टिक्युलर व्हॅल्यूला किंवा त्या पर्टिक्युलर डिफरन्सला म्हणतात नॉइज मार्जिन. Right? So basically noise margin is given by NMH, that is high noise margin, minus low noise margin, NML. Now how to find out NMH, that is high noise margin? So basically it is a difference between VOH minus VIH, and for a low noise margin it is a difference between VIH minus VOL. Okay, so this particular thing is about noise margin. Now coming to the dynamic behavior, as we have studied, for to calculate or to check the performance of any particular device, in our case it's a CMOS inverter, we have to go for it's a dynamic analysis or dynamic behavior analysis. So in that, what we are actually going to do, we are going to calculate different capacitances, right, different delays involved in the circuit operation. So that part we are going to calculate. So regarding this MOS transistor, there are certain capacitances involved. Basically there are two categories of capacitances, extrinsic and intrinsic capacitance. So this extrinsic capacitance are what, which are shown in the figure: the capacitance between source and gate, the capacitance between gain and rate, some capacitance is involved between the bulk and drain, bulk and source, and bulk and gate. Right? That means within each region or each part of MOS transistor, there are certain capacitance are involved. Because see, as I told you, if you uh, draw a general structure of MOS capacitance, so it somewhat resembles with the two parallel plate capacitance structure, right? It is somewhat resembles with the two parallel plate capacitance structure, means one is a negatively charged, another is a positively charged. So that's very generalized structure of MOS transistor. So these many capacitance are involved with a single device. Now if you consider the cascade, right, or there are two or more devices connected in series again with number of stages, now it forms the cascade capacitances. Now you have to consider all these capacitance in that particular device regards, and you have to get the addition of that, right? So there is a drain out, the capacitances between gate and drain, that can or drain and bulk, right? These two capacitance can contribute or can hamper the output, right? These are the drain of driving inverter. Now the gate source capacitance, gate drain, and gate to bulk capacitance, these capacitance can hamper towards the input of inverter. And the, of course there is a wiring capacitance also, right, which can connect the output of the first stage to the out input towards input of the next stage. In that between the wire, whatever the wire that you have connected, so that wire also has some parasitic capacitance, right? So these points you should remember while studying the dynamic behavior of CMOS inverter. Now we have discussed second part is the delays, right? You should consider a propagation delay also. What do you mean by propagation delay? So propagation delay is the amount of time that it takes for a change in input signal to produce a change in the output signal, right? Change in the input signal to produce the change in the output signal. That means इनपुट चेंज झालं की किती वेळाने आउटपुट चेंज होतं. इनपुट चेंज झालं की किती वेळाने आउटपुट चेंज होतं. दॅट particular difference or the difference between that time is known as propagation delay. बरोबर, इट इज एक्सपेक्टेड दॅट propagation should be very less. का? नाही तर असं होईल की इनपुट चेंज झालं आणि तासाने आउटपुट चेंज होते. काय उपयोग आहे का त्याचा? नो, नो. सो as soon as the input changes or input uh, changes its state from maybe high to low or low to high, it should immediately reflect on the output also, depending upon your circuit condition, right? It should immediately replicate on the output side. That means that shows there is a minimum amount of, or there is a actually null propagation delay, and that is what expected, right? So how to calculate this propagation delay? So it's a TPD is equal to max of high to low propagation time and low to high propagation time. It's a maximum of high to low or low to high propagation time. That is called as propagation delay. And what is formula to calculate this propagation delay is equal to K. It's a proportionality constant multiplied by CL divided by VDD in bracket 1 upon beta n plus 1 upon beta p. What is beta? It's a beta ratio. It's a width of n MOS divided by length of NMOS. Beta n is equal to what? Wn divided by Ln. That means width of n channel MOSFET divided by length of n channel MOSFET. So this formula can get you the exact value of propagation delay, right? Now coming towards the next point of discussion is the power consumption analysis of CMOS circuit, right? See, as we are discussing here CMOS circuit, so what are different power consumptions that CMOS, the what are different what we can say the categories of power that is consumed by the CMOS circuit. So basically there is a static power dissipation and dynamic power dissipation, right? So in case of static power, what is cause of this static power dissipation? So it is caused by the leakage current and other static current, right? So basically this particular power dissipation, static power dissipation, is caused by the leakage current and other static current. Okay. Now second is a dynamic power dissipation. What is a reason? What is reason behind this dynamic power dissipation? So basically this dynamic power dissipation, it is caused by the total output capacitance and also it is caused by the short circuit currents, right? So point you should remember is static power dissipation, it is caused by the leakage current and other static currents, and dynamic power dissipation, it is caused by the output capacitance and short circuit currents. Okay. Now how to calculate the total power consumption? So PT, that is total power consumption, is equal to PS plus PSW plus PSC. Now what is PS? It's a static power or leakage power. PSW is nothing but the switching power, and PSC is equal to short circuit power. This switching power can be known as the actually the dynamic power dissipation caused by the output capacitance, that can be known as the switching power. So basically this PT is equal to static power dissipation plus dynamic power dissipation. So in dynamic power dissipation, it can be a switching power dissipation and short circuit power dissipation. So total power is equal to PS plus PSW plus PSC, where this PS is a static power or leakage power, PSW is equal to switching power, and PSC is equal to short circuit power. Okay, so this is about the power consumption. Now again we will discuss in depth about the how actually the static power, right? So now you know, right? What is cause behind the static power dissipation? The leakage current and other unwanted currents, right? So this static power dissipation is major contributed by the reverse bias leakage current between diffusion region and the substrate and subthreshold conduction, right? Now where this leakage current comes into picture, right, that is causing the static power dissipation. So the major contributing leakage current in this static power dissipation is reverse bias leakage current between the diffusion region and the substrate and subthreshold conduction. Now how to calculate this? So the given formula is here. PS, that is static power dissipation, is equal to summation of 1 to n leakage current multiplied by supply voltage. Okay, so this formula where n is equal to number of devices, how many number of devices that you have connected, maybe in a cascade, maybe in a series or parallel condition, doesn't matter. So you can calculate the static power is equal to I leakage multiplied by supply voltage. That will give the exact figure for the static power dissipation. And remember, who are the major contributors, right, in this static power dissipations? Leakage currents. But what kind of leakage current? So it's a reverse bias leakage current between diffusion region and substrate, right? It's a reverse bias leakage current between the diffusion region and substrate. Clear? Now dynamic power dissipation. As you know, what is cause behind dynamic power dissipation? First one is the output capacitances and short circuit currents. So this switching power, or in other words, for this dynamic power dissipation caused by the output capacitance, you can say it's a switching power dissipation. So basically, it is caused by the charging and discharging of the output capacitive load, right? Whatever the output capacitive load as shown in figure, right? So basically this kind of output power dissipation is caused by the charging or discharging of the output capacitive load. Okay, so whenever you can say it's a switching power, so it is mostly because of the output capacitive load, whatever the capacitance that comes into picture. See, whenever you have what we can say, to connect the output of a particular stage to the input of next stage, there involved some sort of parasitic capacitance or wire capacitance, right? And similarly there is a capacitive load also. So this particular switching power, it is caused by the charging and discharging the output capacitive load. Okay, now if you consider an frequency, right, in which the inverter operates, f is equal to 1 by t. This is a very common formula. Now how to calculate this dynamic power dissipation? So it is equal to cpd plus cl, that is the capacitive load. What is cpd? It's a power dissipation capacitance, okay, and specified by the device manufacturer around 20 to 24 picofarad. That means this power dissipation capacitance, the manufacturer of that particular device or that particular CMOS inverter, they will specify, because they know what kind of metal oxide thickness, what, how much amount of p type n type diffusion region, how much polysilicon they have used. So every parameter they knows, and they will specify a particular value of the power dissipation capacitance, cpd, right? So to calculate the dynamic power, cpd plus cl, what is cl? It's a load capacitance into vcc square multiplied by frequency. Vcc is nothing but the power supply voltage, and f is in the transition frequency of output signal. F is the transition frequency of output signal. So by knowing these all values and putting into the above formula, you can easily calculate the dynamic power dissipation, right? You can easily calculate the dynamic power dissipation. Now What about short circuit power dissipation? Okay, now see, this is the second major contributor into the dynamic power dissipation, that is short circuit power dissipation. So what is a reason behind this short circuit power dissipation? So even if there is a no load capacitance on the output of the inverter, the parasites are negligible. The gate still dissipates some switching energy. If the input changes slowly, both the NMOS and PMOS transistors are on and excess power is dissipated due to the short circuit current. That means, see, while studying the VI characteristics, you saw one point where the both NMOS and PMOS are in saturation region. That means they are on actually, right? So in that case, it is as good as the both are short circuited, right? They both are short circuited, and that causes some power to be dissipated due to the short circuit current, right? And if this input and output changes very slowly, right, that means both NMOS PMOS transistors are on at a certain point, and that causes the power to dissipate, right? And that power dissipation is called as short circuit current, right? So how to minimize this? So the simple logic is, you have to keep the switching of input signal as fast as you can, right? You have to keep the input of switching signal as fast as you can, so that the this short circuit power dissipation can be minimized, right? So that the short circuit power dissipation can be minimized. Now, how to estimate or how to calculate the short circuit power? So PSC, short circuit, is equal to I mean, that means mean of the that particular leakage current, mean value of that short circuit leakage current multiplied by supply voltage, that is VDD. This is formula that you can use to calculate the short circuit power dissipation, right? So this is about the power consumption analysis of CMOS inverter. Okay, so the next part is the impact of technology scaling on CMOS inverter. So basically, this part we will discuss in the next lecture. For today, we will stop here. Uh, this will be the last part of your syllabus, impact of technology scaling. So this part we will discuss in the next lecture. For today, we will stop here. If you have any query or doubt, you can ask me right now.
No query, sir.